Hello everyone, my name is Ali Mohammedi and today I'm honored to present my research on advanced cyberattack detection in the Internet of Medical Things or IoMT using convolutional neural networks at the Iranian Conference on Intelligent Systems. This research addresses the growing cybersecurity challenges in IoMT environments which are becoming increasingly important as more medical devices are integrated into healthcare systems. IoMT, or the Internet of Medical Things, refers to the network of interconnected medical devices that share data and play a crucial role in patient monitoring, diagnostics, and treatment. As IoMT becomes more widely spread, cybersecurity becomes a critical concern. This figure illustrates how IoMT integrates various medical devices into healthcare systems. At the center, we have a health app that connects different devices and entities, such as wearable devices, smart wheelchair, and diabetic devices. These devices constantly monitor patient data, which is then shared with healthcare professionals like doctors and hospitals. Traditional security methods are struggling to keep up with the evolving and sophisticated nature of cyberattacks in IoT environments. This is where advanced approaches like convolutional neural network or CNNs come in. In this presentation, I will discuss how CNNs can significantly improve cyberattack detection in IoT networks. IoT cybersecurity faces several challenges. First, scalability. The large amount of data generated by IoT devices make it difficult for traditional security systems to handle. Second, many IoT devices are resource constrained. They lack the processing power and memory to run sophisticated security solutions. Lastly, traditional security methods like rule-based systems often produce false positive and are not context-aware. This makes them ineffective in the dynamic and complex IoT landscape. These challenges highlight the need for more advanced solutions like CNNs. The dataset used for this study is called IOMT 2024. It contains network traffic data from 40 different IoT devices, both real and simulated, and includes 18 distinct types of cyber attack. These attacks range from DDoS and DOS, uh, MQTT specific, and spoofing attack. This dataset is a benchmark in cybersecurity research and offers a comprehensive view of the types of threats faced by IoT systems. This table summarizes the distribution of instances in the CIOMT 2024 dataset. Benign class, which is this one, around 230,000 instances. Attack classes divided into several categories. Uh, spoofing about this one. Spoofing about 18,000 instances of ARP spoofing. Recon for the scan with roughly 107,000 instances, which is this one. MQTT, the largest attack in the DOS, Connect Flood with around 215,000 instances, which is this one. And DOS UDP flood had close to 705,000 instances, which is this one. And DDoS UDP flood dominates with almost 2 million instances. This distribution serves as the foundation of training the CNN model for cyber attack detection. In this slide, I just want to say that it was the really huge data set, and the process of that and work on that could be challenging. Nine and Now let's look at the architect of CNN's model we use. The model is built with two uh, 1D convolutional layers, each followed by max pooling layers. The first convolutional layer has 32 filters, which the second has 64 filters. A ReLU, a commonly used activation function, is applied after each layer to introduce non-linearity and help the model to learn complex patterns. These layers are followed by fully connected layers where the final output layer uses the softmax function to classify the input into one of the 18 attack types. This architect is optimized for analyzing network traffic data and detecting cyberattacks. In summary, first convolutional layer has 32 filters and the filter size is 3, and we use activation function and we use ReLU activation function, and the purpose was extract the local pattern and important feature from the input data. And the purpose of using ReLU was introduce non-linearity, helping the model to learn complex patterns. And for second convolutional layer, the number of filter is 64 and the filter size is 3. And the purpose was uh, further refines the feature extracted by the first layer, enabling the model to detect more uh, abstract patterns. As you can see, after each convolutional layer, we applied max pooling layer. And the purpose of using max pooling layer was reduce the dimensionality of the feature maps, which helps decrease computational cost and control overfitting a specific class. And after flattening the pooled feature maps, two denses uh, fully connected layer are added. The purpose was combines feature extracted from previous layers and enables the model to learn complex representation and decision boundaries. And for the last one, uh, I mean the output layer, the purpose of using that was produces a probability distribution over the classes. This figure shows the performance of different machine learning models across classification tests with 2, 6, and 19 classes. The metrics evaluated include accuracy, precision, recall, and F1 score. So accuracy, of precision, recall, and F1 score uh, are some metrics which show how well model works. And in the accuracy chart, we have in the accuracy chart, our proposed model outperforms the other models, specifically in two class scenario, achieving nearly 100 accuracy, 100% accuracy. As we move to 6 and 19 classes, the performance slightly decreased, but it still remains competitive. Other models, such as Autobus and Random Forest, show a notable drop in performance with more classes. The persistent chart reveals a similar trend. Our model achieved high precision across all class numbers. However, random forest and logistic regression struggle with 6 classes and 19 classes case, as indicated by the red arrows highlighting the significant drops in performance. For recall, the proposed model maintains uh, a very good performance across all class numbers. Once again, we see significant drop in recall for random forest and Autobus. as the complexity increase, which I mean in 6 classes and 19 classes. Finally, the F1 score plot shows that our model outperforms other in all scenarios, particularly in the 19 class test. Random forest has the most significant performance decrease, reaching a low of 47% marked in red. Overall, this figure demonstrates that our proposed model generalized well across various class configurations, and our model can significantly improve the results and performance of other traditional machine learning model, including AdaBoost or random forest or logistic regression. This table follows the same pattern as the previous slide's figure, so I won't repeat the explanation. The purpose here is simply to provide the exact numerical values for each model's performance. So you can check that our model outperformed other machine learning models. And also you can check the exact number of each model in the classification task. This figure 5, presents the confusion matrix for the binary classification task. The matrix helps visual the performance by showing the distribution of true positive, true negative, false positive, and false negative results. The majority of attacks are correctly identified, while a small portion of benign traffic is misclassified as attacks. The sixth class classification task involved distinguishing between 5 types of DDoS and DOS attacks alongside benign traffic. The model achieved high F1 score of most attack types with slight misclassification in category like MQTT DDoS, publish flood, and MQTT malformed data as reflected in Figure 6. For the most complex task involving 18 different attack types, the CNN model demonstrates strong overall accuracy of 99% as depicted in Figure 7. However, classes like spoofing and recon can presented more challenges for the model with slightly lower precision and recall values compared to the DDoS and DOS classes. In conclusion, the CNN-based model we presented is highly effective for detecting cyber attack in IoMT environment. It outperforms traditional machine learning models, which was used in previous papers in both accuracy and precision, specifically in multi-class classification task. However, there is still room for improvement. For example, detecting certain low support attack types like spoofing can be challenging, and future research could focus on improving feature extraction techniques and a model architect. Thank you all for your time and attention. I hope this presentation provided a valuable insight into the dataset and our approach to cyber attack detection using machine learning techniques. If you have any question or need further clarification, feel free to ask. I'm happy to discuss this further. Thank you.